Hey guys, Mr. Backerwick here. In this video, we're going to look at other algorithms. So the rule that we're going to focus on is called Simpson's rule. So if we want to approximate the integral of some function f of x dx from a to b, then Simpson's rule, or S, says that we're going to take h over 3 and multiply it by a whole bunch of y values, similar to what we did with our trapezoidal rule. Now notice the first and the last y value don't have any multipliers on them, but then in the middle we alternate between multiplying by 4 and multiplying by 2 every other term. Now to use Simpson's rule, we need our a to b interval to be partitioned into an even number, n, subintervals of equal length, where we get h by doing b minus a over the number of intervals that we're making. And in class, I'll give you guys a Simpson's rule program for your calculator. So in this example, we're going to use Simpson's rule with an n value of 4 to help us approximate the integral of 5x to the 4th dx from 0 to 2. Now the first thing I want to find is my h value. And to do that, we take our upper limit minus our lower limit and then divide by the n value that we've got. So our upper limit was 2, our lower limit was 0, and we've got an n value of 4. So that gives me an h value of 1/2 if we reduce that down. Now the next thing we need to do is come up with our y values. So I'm going to make a quick x and y table. So we're starting at 0, and we're making half steps until we get to 2. So if I add a half to 0, then I'll get a half. If I go another half step, I'll get 1. Another half step is going to be 3 halves, and then another half step will be 2. Now I need to take all of those x values and plug them into this 5x to the 4th. Well, if I plug in 0, I'm going to get 0. If I plug in a half, I'm going to end up getting 5/16. Plugging in 1, I'll get 5. Plugging in that 3 halves, I'm going to get 405 over 16. And then lastly, plugging in 2, I'm going to get 80. Now using Simpson's rule, it says that we're supposed to take our h value over 3 and then multiply by our y values. So our first y value and then our second y value gets a 4 multiplier on it. My third y value gets a 2 multiplier on it. My next y value gets a 4 multiplier on it. And my last y value doesn't get any multiplier on it at all. So in here, if I take 1/2, that h value, and divide it by 3, or multiply it by 1/3, then I'm going to get 1/6 times that first y value is 0, and then 4 times that next y value, which is 5/16, and then 2 times that next y value, which is 5, and then 4 times that next y value, which is 405 over 16, and then my last y value of 80 doesn't get any multiplier on it at all. Now if I do all of this multiplying and adding, we're going to end up getting 385 over 12. Now I want to take that answer and compare it to the true integral. Now I notice there's a 5 multiplier on here, so I'm going to pull the 5 out front, and then I'm going to do my anti-power rule. So I've got this x being raised to the 4th, so I want to do 1 over the power plus 1. So that's going to be 5, and then I multiply that by x, and then I add 1 to the power, so I get x to the 5th. Now this 5 times 1/5, those 5s cancel each other out, and then we just end up with that 1x to the 5th. So the antiderivative is just x to the 5th. Now evaluating this integral, I'm going to plug in the 2. 2 to the 5th power is 32, and then I'm going to plug in the 0. 0 to the 5th power is 0, and I subtract those, so I get an answer of just 32. Now the difference between these is actually just 1/12. So by using only 4 subintervals, our percentage error is less than 0.3%. And naturally, if we used a bigger n value or more subintervals, we would get a more accurate answer. That's going to be it for this video. Thanks for watching.